with that demonstration, we learn a poor bending today. Poor bending. And let me redraw what we saw in that demonstration. If we have a member, there, and the longitudinal axis, or we can say the neutral axis, go through the member here, the neutral axis. Here, if I apply a bending moment, so that in this case, clockwise on the left and counterclockwise on the right. And with that, as you can see with the stripe that I showed in the demonstration, it's 7 centimeter. And then when the moment apply, the member, it will be bended. It's shown here. And with that bending, the light in the middle, the neutral axis, that in neutral axis, and the stripe, as you already see, it basically become like that. And yes, after a bending moment, the shape is displayed. So in this case, we call that here displays shape after the bending moment applied on that member. And with that, several assumptions for the poor bending need to apply before we continue the assumption. What are the assumptions we need to make? There are 4 assumptions. The first one is beam initially straight. Beam initially straight. The second assumption we need to be make is plane section remain plane, so no distortion on the section. So plane section remains plane before and after the bending moment apply on. And same as in torsion, we want a constant cross section throughout. And the last one, even I exaggerate with that display shape here, but in the real life, and I put it here, small deformation, just like in torsion, we want small distortion, angular distortion. In this case, small deformation. So that the small angle, when it's small angle, we can use something like before, angle in radians approximately equal to tangent of that angles and approximately angle to side of that angle. So it will have a small angle. Small angles. Let me write down here angle. Going to the width. So that is a poor bending. So with that, let's make a section that between the stripe, and that I call that is delta x. The distance between the stripe is delta x. For example, I show you 7 centimeter, but just make a smaller one here and go to the right finger that I already prepare and copy from your textbooks, that resolve the neutral axis is in the middle. It also depends on, it don't have to be in the middle, depend on the cross section. If it's circle, it absolutely it will be in the middle. Because neutral axis, by definition, if you recall, it go through the centroid of the member, right, and parallel to x or y axis, and that neutral axis. So if the cross section is not symmetrical, like square or rectangle or circle, then the neutral axis may be not at the center in there. So with that, as you can see with the demonstration, the middle one, the neutral axis still remain unchanged in terms of the distance after the bending. So the delta x remain unchanged in the middle. And with that one, and the top, it will be contract. So let me make a parallel line, parallel line from the intersection of the point on the BB apostrophe parallel to AA apostrophe on the other side. So let's make that parallel line. From the neutral axis cross to BB apostrophe and parallel to A. So what we have with that parallel, we have this distance between B and the intersection of that point. We call that is delta C, that is deformation at the outermost fiber. And of course, with that parallel, we will see A apostrophe to that point here. It will be the same delta x, the same delta x. And let's call the distance from the neutral axis to the outermost fiber is C. From the neutral axis, let's call that distance, neutral axis to the outermost fiber here. We call that is C. Just something we also learned that in that is C. Learn in torsion. And we also have on the other side, we also have the distance for that one here, also C. And let's get certain definition in here before we move on. So first, the NS, as you already know, NA in neutral axis. Now if NS, then it basically neutral surface. Neutral surface. So it's neutral surface, similar to neutral axis, is a surface, but it goes through the centroid of the cross section and parallel to x or y. In this case, as you can see, parallel to the longitudinal axis. And with the neutral surface, and you can see that it go through the centroid, and I put it delta x here. If it's in the middle there, it does not change the length, and I demonstrate with the noodle. With the noodle, does not change length. With the poor bending, it only change the length on the top, which is compress or contract AB, and then it extend, and the bottom with that poor bending as shown, it extend, and the A apostrophe B apostrophe, it will be bigger than AB as I shown in that finger. And then C, as I mentioned earlier, that is the distance to the outermost fiber. The distance to the outermost fiber. And it can be distance go down to B apostrophe, or from the neutral axis go through B. that C distance from the outermost fiber. So with that definition, we have a few things here. So as you can see, if I call any position between the neutral axis and outermost fiber, the distance from the neutral surface to that point that I call it y, and the displacement at that point y, it will be delta y. So at any point located y from the neutral surface, they have a corresponding displacement delta y, deformation delta y. So with that, with the similar triangles there, that similar triangles, so we can have what? Just write down here, from similar triangles in the small on the right side that I just draw. So from similar triangles, what we have is that you can see here the delta y over y equal to delta c, which is the deformation at the outermost fiber, divided by the distance c from outermost fiber to the surface. Okay, distance from the neutral axis, neutral surface to the outermost fiber. With that said, I can write down here, we have it delta y in over y equal to delta c, the displacement or deformation at the outermost fiber, over the distance from the neutral axis to outermost fiber. And with that, what do we have? We have a few transformation. First, recall in terms of normal strength. Normal. Everyone recall what is normal strength is? You see normal, so it create normal strength create due to the normal stress, so it epsilon. And epsilon, if you recall, it equal to the deformation divided by L naught, the original length. So from that, the deformation we will have equal to epsilon L naught. So nothing new in there. So with that same information, I can apply that for delta y and delta c. So with that equation, I can have delta y equal to the normal strength at that position y times the original length L naught. And as we have the original length is delta x, because we cut a delta x from the member in bending and zoom in with that delta x, so that the original length is delta x. So from that, I can have this one equal to epsilon y, normal strength at position y from the neutral surface, times the original length delta x. And of course, similarly, I have delta c equal to epsilon c, the normal strength at the outermost fiber, times L naught. In this case, L naught equal to delta x, so it will be epsilon c times delta x. Everyone good so far? So from that, we can replace that into the equation delta y over y equal to delta c over c. So what we have here is plug in, we can have delta y, so which is epsilon y delta x divided by y equal to epsilon c delta x divided by c. And of course, we can eliminate delta x at both sides. So what we have here is we basically have epsilon y over y equal to epsilon c over c, and that, let's box that equation here. Okay, so what we can observe, and you can see the with that relationship, the normal strain have a linear distribution because it depends on only c is constant. If it's consistent constant cross section, c the same, only the change is the y, and you can see, and with that it's linear, right? Y is no power on the y, so that will have a linear strain distribution. So from that equation, so we can draw the strain distribution in that body, there. If we have a moment applied and we have a neutral surface NS, neutral surface NS, then the normal strain, it will be linear. So what does that mean? Undo that, not correct drawing. So it start from here 0, go down bigger, go left in there. So that basically the normal strain, and in this case, as you can see, the top is compressed, so it will be contract the length, the bottom through the neutral axis 0, then it extended at the bottom if the moment applied that way, and that we call is the normal strain due to bending. So unlike the axial loaded member, you remember cow member, centroid axial loaded member, the normal strain is the same throughout cross section, but with the bending moment it also creates the normal strain, but it can be contraction or can be extension. In this case, as you can see, it contract on the top and extend the length at the bottom with that moment, and the normal strain distributed linearly throughout the cross section. So let me write down here linear strain distribution. So it's straight line, right? Strain distribution. So that's the first thing we learned for the poor bending. The next we will discuss about the normal stress.